I suppose we should talk about limits at infinity then. They're one of my favorite parts of teaching limits. I really like them because I get to use the infinity symbol a lot, and I find it very satisfying to draw it. Maybe you do too. And I like them because like I get to like plug in infinity and deal with infinity as if it were a number and like do the stuff that seems like a horrible abuse of notation, and it is, but it works and it's really cool. We do need to talk about the notation. So the only thing that tells us that we're working at a limit at infinity is that, well, I've got infinity at the place that x is going to, right? So like the infinity lives downstairs underneath the limit symbol, unless it's inline math, and then it could be like below and to the right a bit. Um, and watch for the sign in infinity. So in particular, pluses and minuses. And these are always only one-sided limits, because if we're talking about infinity being out here, you can only reach infinity from the left. So here are two preview limit at infinity problems. And I want to go ahead and talk through these both with you right now. And then we'll come back and dig in more detail. I'm going to work through problem A with you first, and then I'll work through problem B. I really like graphing as a primary method of investigating limits. And so I just want to get a handle on what's going on for the function in limit A. And so what I like to do, and I'd like you to do this along with me, please, to continue getting more practice in plotting functions, is and using your calculator as a tool to solve these problems, because I think if you're not using your calculator, you're not doing it right. So let's plot this function and work along with me now. So I'm going to go 20x squared minus 3x, div, open a paren, 3x squared minus 4, oh, that was supposed to be to the fifth, I do apologize, 3x to the fifth minus 4x squared plus 5. Let's take a peek and make sure that I entered it correctly. 20x squared minus 3x fifth, yes. Okay. So now I'm going to go zoom, and I'm going to go to the standard window, 6. Does yours look about like that? I hope so. The easy mistakes to make on graphing problems like this are to forget parentheses to group the things in the numerator and denominator. So I'm going to keep using this on-screen calculator to help reinforce the necessity of of parentheses to make things happen the right way. So one thing I want you to notice is like what's going on over here on the right-hand side. So over here on the right-hand side where that moving dot is, look what's happening to the y values. Anybody want to propose a value for what they think the value of this limit is? Feel free to just type it in the chat. You receive no judgment. Yeah. It's going infinitely to 0. It's going to 0, definitely. Yeah, when you say it's going infinitely to 0, I'm curious about what does the infinitely part mean to you? I think it's good to just like focus on the language that we use. What do you mean by going infinitely to 0? I would say it's going asymptotically to 0, because there's an asymptote, right? I've got my function. Let's go ahead and transcribe it. I've got my function. And so there is a horizontal asymptote over here, right? And so when the function is heading to 0, I would say f tends to 0 asymptotically as x goes to infinity. And that's a sentence that I would utter. So that's a good word. Thank you so much for explaining, and I'm glad I was able to give you a new word today. So let's take a look at this other one. I want to know about this other function here. Let's check out function b, and I want to do that again with my calculator. Maybe it's been a little while since you've played with e to the, and so I'll try to point out the function for it. So we'll go 17.4 divided by, opportunity for a mistake, forgetting to put an open paren right there, 1 plus 5.56 times e to the, there's no way you can read that symbol, but it's underneath the ln button. And it's that way on both of the TI calculators in front of me. So I'll go second ln to get the e to them. Then I'll go minus 0.022, and then instead of TI of x. Let's start with the standard window on this one also. And there's some instruction on this one that I want to specifically engage with you. So I got zoom 6, and this is the view that I get. And my function looks like that. And the question is, what's happening to it? Is it going to infinity? Is it gonna like, is it gonna like, like what's gonna happen? Is it gonna stay linear like that forever? I think we should change our window. So let's do window. Let's change x min to be 0. And let's go x max. Let's make that be like, I don't know, let's do 100. Let's go x scale is 10. And let's graph it. Now, I'm guessing on yours, if you just manually adjust the window like that, then we probably don't get any plot. And so you probably need to now go zoom fit to adjust the vertical scale for you. This function looks like it keeps going up. Looks like it's getting steeper. Let's change our window again. Let's go to 1,000. And let's make our scale be 100. So we're going from 0 to 1,000. X scale is 100. And the X scale is 100. That puts the tick marks. So I'm going to try it again. Okay, so we're going from 0 to 1,000, 0 to 30, graph. What? 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 Oh, what a function. And it levels out. How curious. What's the height of it? Use trace. Use trace. What's the height of that function? What do you think the value of that limit is? I think it's 17.4. This is another one where it would go asymptotically to 17.4. I wanted to do this problem B, because it shows you that the graph can be a great tool, but it can be misleading. And so we should have additional techniques that don't depend just on graphing. And you should just be really careful about the way that you use graphs, particularly at infinity, because sometimes stuff doesn't happen until like, x equals 100, that like the interesting stuff finally happens. So I hope that serves as a good lesson as you work through doing limited infinity problems.